Many of us have seen representations of the solar system in educational materials, with the sun slightly larger than Jupiter. However, this illustration does not accurately capture the true scale. The sun is so immense that we could fit around 1,000 Jupiters inside it. Despite being impressive, our sun is not the largest known star in the universe, not even in our own galaxy. That title belongs to Jessicamftrovao, making our star just a small stone in comparison. However, there is something even more intriguing. Scientists have come across an ancient and enigmatic star that harbors a black hole inside. If you like this type of subject and want to learn more from us, I ask you to subscribe to our channel and leave a like. It will help to create more content like this. This astronomical phenomenon challenges scientists' understanding and could potentially explain the formation of the universe as we know it today. But how is it possible for a black hole to exist inside a star? Why were these stars so gigantic? And what would happen if a star with a black hole entered the solar system? Stars are like cosmic forges. In their incandescent cores, they manufacture most of the elements present in the universe. However, the stars that could have arisen in the early stages of the universe were something completely different. Instead of possessing conventional stellar cores, they housed black holes, allowing them to expand to unimaginable dimensions and beyond. Ordinary stars form from clouds of gas and dust, where gravity causes the denser regions of these clouds to collapse. The resulting mass heats up and gives rise to a protostar, an early stage in stellar evolution. Over time, the newly formed hot core accumulates enough matter from the rotating disk of gas around it to become a main sequence star, which then produces energy through nuclear fusion. Our Sun took about 50 million years to reach this phase. Most stars will spend most of their lives as main sequence stars. However, eventually they will all become white dwarfs if their mass is not large enough, or they will undergo supernovae. The exact fate of a star after it explodes depends on its mass. When our Sun uses up its hydrogen supply in about 5 billion years, it will turn into a red giant. We can say that it will expand to about 200 times its current size, before finally losing its outer layers and becoming a white dwarf. A white dwarf is a celestial object that is about 200,000 times denser than Earth, but of similar size. This dense sphere will slowly cool until it reaches approximately 18 million degrees Fahrenheit, 10 million degrees Celsius, and in about 10 billion years, the Sun's resulting white dwarf will crystallize. This process is similar to the formation of ice from water, although the materials involved are different. In the case of the Sun, it will be the solidification of carbon and oxygen. Our stars with a mass greater than 10 times to reach that of the Sun follow a different fate. Most stars will spend most of their lives to collapse after a supernova. However, they are not massive enough to become white dwarfs if their mass is not large enough. Deep within these stars, they will undergo extreme pressure compresses the exact fate of a star after it explodes depends on its mass. That they fuse when our Sun uses up its hydrogen supply in about 5 billion years, it will turn into a red giant. Resist gravitational pressure. We can say that it will expand to about 200 times its current size. Neutron stars are the finally losing its outer layers and becoming a white dwarf. A white dwarf is a celestial object that is about 200,000 times denser than Earth, they still carry a mass equivalent to that of the Sun. This dense sphere will slowly cool until it reaches approximately 18 million degrees Fahrenheit, sugar cube 10 million degrees Celsius, and in about 10 billion years. Let's understand how stars turn into black holes. This process is similar to the formation of ice from water, although the materials involved are different. Fusion, and in the case of the gravity resulting, it will be the solidification of carbon and oxygen. When there is no more fuel to power nuclear fusion, the star no longer has the strength to resist gravity. Thus, it collapses in on itself, similar to the controlled demolition of a concrete building. Einstein proposed that any object with enough mass and compressed within a specific radius could become a black hole. Black holes continue to grow over time, absorbing any matter that comes too close. This creates a region where the gravitational force is so intense that nothing can escape, and the black hole consumes even more nearby material. This is an analogy to the sinking of the ground due to the collapse of underground structures. However, with black holes, it is a gravitational sinkhole that gradually accelerates as its event horizon grows. Generally, black holes have a limit on how fast they can grow, determined by the Eddington luminosity limit. This limit occurs when a black hole cannot absorb material any faster than it already does. It's like filling a car tire with air. If it's inflated quickly, some of the excess air escapes. In space, something similar happens with rotating black holes. As matter spirals toward a black hole, its speed increases, allowing about 42% of it to be converted into energy. This radiation is so powerful that it can repel some oncoming material, like a car tire pushing air away. This process is so efficient that the radiation emitted surpasses the energy production by nuclear fusion in stars. Imagine a future where we can use this energy for our needs. Our sun took about 50 million years to reach have a large surface area. Most to stars will spend most of their lives as main sequence They reside stars. At the center of virtually all galaxies. They will all become white dwarfs. It was recently discovered that some of these supermassive black holes or they will undergo larger than previously thought. The exact fate of a star phenomenon represents one of the greatest mysteries in astronomy. When our sun uses up the hydrogen supply in about matter over the age of the universe, it will turn into a red giant. To explain its colossal size. We can say that it will expand to about 200 times its current aspect that can solve the enigma. Finally losing its outer layers or near stars becoming a white holes must have been the largest celestial object that is about 200,000 times denser than largest black of similar size to date. This currently sphere will slowly in the universe until it reaches approximately 18 million degrees Fahrenheit. But at the beginning of time, space was filled with about 10 billion years of gas. The sun's resulting white dwarfs will crystallize. Material collapse under its own gravity, the formation of ice from water, and giving rise to materials and stars are extraordinary magnitude. In the case of the sun, there is a theory that these stars may have originated from dark matter halos, spherical regions of dark matter, with masses up to 100 million times that of the sun, where thousands of supermassive stars could form. Normally, large stars would end up going supernova and leaving behind huge black holes. However, these celestial giants were not just big, but so big that their size allowed them to absorb the explosive energy that would normally expel the star's outer layers into space. As a result, these ancient stars experienced implosions that turned their cores into small black holes while leaving the outer layers intact. If you could observe this phenomenon up close, you would hardly notice any change in the star. Now, with a baby black hole inside a quasi-star, the consumption process begins from the inside out. At this stage, the black hole is small but rotating, creating a disk of extremely hot material that surrounds it at almost the speed of light. Additionally, there is no limit to how quickly it can consume gas, as the pressure from the star pushes it directly into the black hole. The friction within this accretion disk becomes increasingly intense, emitting large amounts of radiation and causing the host star to shine brightly, like a small galaxy. Our sun took about 50 million years to reach this phase. Faster than most stars will spend most of their lives as main sequence stars. Over millions of years. Eventually they will all become the largest stars if their mass is not large enough size, or they will undergo supernovae. The exact fate of a star after it explodes depends on its mass. These near stars may have ranged hydrogen supply in about 5 billion years to potentially equaling the diameter of our solar system. We can say that it will expand to about 200 times its current size dimensions before finally losing its outer layers. The larger these quasi-stars become, the shorter their lifespan. Is a celestial object that is about 200,000 times denser than Earth, 4 billion similar size, with about 6 billion years left in its life until it reaches approximately 18 million degrees Fahrenheit, 10 million degrees Celsius, spectacularly, and in about 10 billion years, the sun's resulting black hole ready to tear through space. This process is similar to the formation of ice from water. What if a star like this wandered through our peaceful celestial neighborhood? In the case of the sun, gravitational influence would disrupt the carbon and orbits of planets and celestial bodies. The planetary system, once ordered, would enter into total chaos, with Earth subjected to an intense rain of asteroids. The effects would be felt even before the near star completely entered our solar system. As the giant star devours the outer planets and other celestial bodies, Earth would experience an increase in temperature and luminosity, making its surface uninhabitable. Eventually, Earth would also be consumed, although life here had already disappeared long before that. The central black holes found within quasi-stars may have acted as a starting point for the formation of the supermassive black holes that today reside in the cores of galaxies. These dynamic processes associated with quasi-stars, such as the collapse of the central black hole and its interaction with the surrounding matter, may have been significant sources of gravitational waves, thus contributing to the formation of galactic structures and the distribution of stars within galaxies. Furthermore, quasi-stars could have important implications for astrobiology, as the intense radiation from these objects could have influenced the habitability of nearby planets, possibly altering life conditions in unforeseen ways. Considering this, in the context of cosmic evolution, quasi-stars may have played a crucial role in shaping the future of the early universe in unimaginable ways. Although it is unlikely that quasi-stars currently exist in our universe, it is possible that small black holes with a mass similar to that of an early asteroid are still present. Theoretically, if these black holes were abundant, they could be drifting through space, occasionally becoming trapped in gas clouds. Then, as new stars form, these primordial black holes can be incorporated into the cores of those stars. Even black holes with a mass similar to Pluto could grow considerably in just a few 100 million years, a relatively short period in terms of stellar evolution. Therefore, it is theoretically possible that even our Sun contains a black hole. Even if it did, we wouldn't even notice it, although it is highly unlikely. However, scientists are considering a method that could aid in identifying these potential cosmic reservoirs of primordial black holes. For one thing, Hawking stars would be notably longer-lived. As they age, Hawking stars expand, turning into red giants, a process that is also reserved for our Sun. However, red giants that harbor a small black hole inside would be slightly cooler than usual. About 500 exceptionally cool red giant stars have already been identified by researchers. To determine whether these stars harbor primordial black holes, scientists plan to observe the stars' characteristic wobbles during their pulses, which could indicate that they are not just ordinary red giants. Additionally, an intriguing theory suggests that the mysterious dark matter that permeates the universe may be composed of a myriad of tiny primordial black holes. While it is highly unlikely that such a small black hole would be captured by a star, the existence of countless numbers of them suggests that at least some could eventually be captured. However, only time will tell, as we are still waiting for the scientific community to discover these phenomena. In the meantime, stay tuned for more fascinating revelations about cosmic mysteries. Share your thoughts on these enigmatic almost stars in the comments below. We read them all. Thanks for watching.